lots of the reactions that we see in chemistry are reversible. And that means that it can go forwards or backwards. So we use a special arrow when we are talking about these reactions that can go forwards and backwards. And that is the equilibrium arrow. So here we have hydrogen gas combining with iodine gas to form 2 hydrogen iodide. So this reaction can go either way. Either the hydrogen and the iodine can collide and form the hydrogen iodide, or the reaction can go backwards and you can get decomposition of the hydrogen iodide into hydrogen and iodine gas. So when we start off, we've only got hydrogen and iodine, and according to our collision theory, it's very likely these are going to collide and that we will get lots of successful collisions between the hydrogen and the iodine. Now, as this reaction goes on and we produce more of the hydrogen iodide, the likelihood that the hydrogen and the iodine will actually collide is going to get less and less. And that means that if you're less likely to get a collision, you're less likely to get a successful collision between the two, and the rate of the forward reaction will slow down. Now, as this reaction proceeds, we start forming more and more hydrogen iodide, and that means that we're more likely to get a collision between 2 molecules of this, and it's more likely to decompose. There's more of it there, so it's more likely to decompose back down into our 2 starting gases. So as the concentration of hydrogen iodide increases, the rate at which it goes back to the hydrogen and the iodine increases also. So as the reaction is proceeding and you are going forward with this equilibrium, your forward rate is slowing down, your backward rate is increasing until the point where both of these rates are going to be the same, they're going to be equal. So you'll reach a point where K1 is equal to K2. And at this point, when you form some hydrogen iodide, you are also decomposing some at the exact same time to reform the hydrogen and the iodine. So the concentrations effectively won't be changing. You've still got the same amount of everything in solution, but you are still moving everything. Things are still reacting. It just looks like nothing's happening. And that's where we get this idea of dynamic equilibrium from. So where you still have a reaction happening, but it's going backwards and forwards. And so it looks like it's staying the same, but it's dynamic, so it's moving. Now, this dynamic equilibrium can only happen in a closed system. If our hydrogen iodide or our hydrogen iodine were allowed to escape, or we were allowed to add other things in here, then that would upset our equilibrium. If you start adding molecules from the air into this, then it's likely that the hydrogen and the iodine will collide with nitrogen instead, and that will slow the forward rate. So these things are very sensitive and can only happen in a closed system where nothing can get in or get out. And remember that at our dynamic equilibrium, our concentrations won't be changing because the forwards and the backwards rates are equal. So what we need to be able to do with this is say how our equilibrium position at our dynamic equilibrium will be affected by various different condition changes. So this could be a change in concentration or a change in pressure or a change in temperature. And we can get the this idea from the Chatelier's principle. So Le Chatelier states that whatever change we apply to a system, so to our equilibrium, the equilibrium will shift in order to counteract that change. So this is very similar if you do biology to homeostasis. So the body recognizes there's a temperature increase, and so it will give effects that lower the temperature of the body again to bring you back to where you're happy. Now, obviously, the dynamic equilibrium isn't thinking. It doesn't know what it's doing, but it does shift the equilibrium in order to counteract these changes. So let's look at an example of sulfur dioxide being oxidized to form SO3. So first off, we're going to say what happens if we increase the concentration of one of these things. So let's say we increase the concentration of O2. So when we increase the concentration of this O2, what we're saying is that now it's more likely that things will collide with O2. We are saying that it's more prevalent within the within our box that we're trapping everything in, because remember the dynamic equilibrium needs to be in a closed system, and we've added more oxygen in there. So because we've added more oxygen in there, we've made it more likely that oxygen will collide with the SO2, or I should say more likely that the SO2 will collide with an oxygen. If we're getting more frequent collisions, that means we're more likely to have a successful collision, and therefore we're more likely to form SO3. So the forward reaction is more likely to occur, and so increasing the concentration of oxygen favors the right-hand side. So if we're to write that up, we can say increasing the concentration of O2 favors the right-hand side of the equilibrium. It shifts the equilibrium to the right-hand side. We can say that that is because SO2 is now more likely to collide with O2. And so a successful collision is more likely to occur, forming more product. So we can also say that increasing the concentration of O2 means the equilibrium position will change in order to decrease the concentration of O2. So we can say, according to Chatellier's principle, I'm just going to say the Chateliers, so I'm just going to say LC. So according to the Chatellier's principle, increasing the concentration of O2 means the equilibrium will shift to decrease the concentration of O2. So this means the equilibrium will shift to the right to use up more O2, forming more product. So we've explained it in two ways there. We've explained it using collision theory and explained it using Chatellier's principle. You can be asked for either. It's more likely that they'll ask you this type of question and ask you to explain what is happening, in which case you would only need to say that according to Chatellier's principle, the equilibrium will shift to the right-hand side to decrease the amount of O2 as the amount of O2 is increased. but it's important to be able to explain why that's happening. So it's okay saying that, according to the Chatelier, this will happen, but we need to be able to explain why it will happen, not just trust that the Chatelier is right. We need to understand what is actually happening, in which case it's more likely that you will collide with the O2 and produce more product. So it's all a statistics game. So the next one is increasing the pressure. So we're going to look at the same reaction, only this time we're going to increase the pressure. So when we increase the pressure, according to the Chatelier's principle, our equilibrium will shift to try decrease the pressure, minimize the change applied to the system. So we can say that when we increase the pressure, the equilibrium will shift to decrease the pressure. This means we will favor the side with the fewest moles of gas. And so in that case, we're going to favor the right-hand side again, because on the right-hand side, we have 2 moles of gas, whereas on the left-hand side, we have 3 moles of gas. So the equilibrium is shifted to the right-hand side, decreasing the pressure, as we now have fewer moles of gas in the same space, and so we've effectively decreased the pressure. So the last example that we need to look through is temperature. So again, we're going to look at the same reaction of the 2SO2, combining with O2 to give us 2SO3. But this time we are told that the forward reaction has an enthalpy change associated with it of minus 197 kilojoules per mole. So remember that a negative enthalpy value tells us that this is an exothermic reaction, and so heat will be given out to the surroundings. So that means that if we were to measure the temperature change, the temperature would increase while the reaction is proceeding. So if the temperature increases, that means the equilibrium is going to shift to the side that lowers the temperature. Okay, so we're going to say that we are going to increase our temperature. So when we increase the temperature, according to the Chatelier's principle, our equilibrium will shift to the side which the reaction lowers the temperature. So remember, that would be the endothermic side, because that means that we will be taking in energy in order for the reaction to proceed. And so it will favor the endothermic reaction, as this is the reaction that takes in energy. So increasing the temperature favors the endothermic reaction in order to lower the temperature. So because our forward reaction is exothermic, that means our backwards reaction must be endothermic. Okay, so our backwards reaction is going to be positive in enthalpy. So this means the equilibrium is shifted to the left. Endothermic side in order to take in energy and lower the temperature. So when we've been through all of these different effects that we can have, obviously doing the opposite thing does the opposite to the equilibrium position. So here we increase the temperature, but lowering the temperature favors the exothermic reaction in order to increase the temperature. This means the equilibrium is shifted to the right-hand side, the exothermic side, in order to release energy and higher the temperature again. So we can say the exact opposite to all the answers that we've written, and depending on whether we are asked to increase or decrease the temperature or the pressure, we just say the opposite to what we've said in the examples we've been through. So it's important to remember as well that catalysts have absolutely no effect on the equilibrium position. So when you have a catalyst, yes, it speeds up the reaction by providing that alternative pathway to the mechanism, but it doesn't affect the equilibrium position at all, because when you've got an equilibrium, it speeds up both the forwards and the backwards reactions. So yes, you are going to get faster reactions, but you're getting faster reactions both ways. And so if we look at something like the Haber process, where we have an iron catalyst, then the iron catalyst being there has no effect on whether we produce more ammonia or more nitrogen and hydrogen. All it means is that the forward rate now and the backwards rate, if we're at dynamic equilibrium, remember they will be the same. It just means they're going to be faster. So without the catalyst, this reaction could take ages to occur. With the catalyst, it happens a lot quicker. You get forwards and backwards reactions happening a lot quicker, but it doesn't affect how much of either thing we have. It doesn't affect how much products or reactants we have, because these rates are sped up by equal amounts, and so it can't ever increase yield. But if we say add some nitrogen into this, so let's say we increase the concentration of N2, then having a catalyst present means that we reach our dynamic equilibrium again a lot quicker. So once the equilibrium is upset, and we have to talk about the Chatelier's principle and how we are going to rebalance the equilibrium. So for increasing the concentration of N2, we would therefore shift the equilibrium to the right-hand side to use up the N2, producing more ammonia. So that rebalancing of the equilibrium will happen a lot quicker with a catalyst present, because your rate of reaction is a lot quicker. So you're going to be moving back to that equilibrium quicker. But it doesn't affect the amount of yield we get. That's only affected by concentration, pressure, or temperature.